Thank you very much for the invitation to come here. I'm very, very glad to give this talk here to the students and lecturers here. So the topic of the talk is challenges in astrophysical imaging. From planetary systems to the Big Bang. I'm going to make a little overview, small overview of many fields that I find very interesting. In these fields, the Institute of Astrophysics in the Canary Islands has developed research, I think, on a great, at a very great level. I will start by describing the role of telescopes and instruments. For perhaps some of you, this is not so obvious. For others, it will be extremely obvious. But I will start with that little introduction, and then I will go into the exploration of the universe, how we do this exploration. As I say, in many of the topics that I will present here, there are many active researchers just 2 kilometers from here, or less than that, in the Institute of Astrophysics, and a few floors up there in the Department of Astrophysics here. So if you are interested in these topics, please contact the researchers, because your career may be associated in the future to any of the things here. But it will be just a brief introduction, okay? So, exploring the universe. We use observatories in ground and also space missions. That's important. We use both to really explore in the optical, in any window of the electromagnetic spectrum. We explore the universe using facilities, as you see here, just a small collection of telescopes, both in space or here in ground. For ground observatories, we do optical, infrared, radio, millimeter, submillimeter. For space missions, we do things that we cannot do from the ground because of the atmosphere. And in particular, we have observatories to explore the solar system, of course, direct missions to visit bodies of the solar system. We have observatories to measure the ultraviolet, optical and infrared. Well, in the infrared, of course, we can do research from ground, but some windows we cannot observe very well from the ground. So Hubble, for instance, do observations in the optical infrared, also into ultraviolet. For X-rays, we have XMM or Chandra, satellites from NASA and ESA. In gamma rays, we have Integral or Fermi, continuously exploring the sky to detect strong emission in these windows of the electromagnetic spectrum. And in the infrared, there are many other satellites. In the past, there was IRAS and ISO. So very recently, WISE and Spitzer and Herschel have been the missions dedicated to explore the far infrared and the near infrared as well. And in the microwaves, the cosmic microwave background missions like COBE in the 90s, WMAP in the past decade, and now Planck. So all that is just to serve our intention to understand the universe. From here, from the Canary Islands, we have one of the best observatories in the world. The Canary Islands host 2 observatories, one in La Palma, you can see here, where it is located, the largest optical infrared telescope, and the other observatory is Teide, where we have one of the largest solar telescopes now in operation, and there are many other facilities for small telescopes. I will describe this in a little bit more detail while we use this little movie. You see the solar towers in the observatory here. This is La Palma. This is one of the optical telescopes, the William Herschel telescope, 4 meter. There is overall more than 20 telescopes in full operation in the observatories here next to you in the Canary Islands. And there is a lot of research going on here, actually, for many countries. As you see, this is real Spanish observatories, but with a large participation of many other countries. Some of the national facilities of other countries are located here in our islands. This is, for instance, one of the telescopes, the 4 meter telescope. In the 90s, this was I think, the most efficient optical telescope in the world. In the middle of the 90s, the Keck 10-meter telescope started operation in Hawaii and became the most competitive telescope. But this William Herschel telescope was, as I say, in the early 90s was, I think, the most competitive telescope in the world. Now, of course, it has been surpassed by other telescopes like our 10-meter telescope, Gran Telescopio Canarias. But this telescope is still in operation and it's doing excellent science. I will show you just as an example instruments that are located in the prime focus of the telescope, which may provide a spectroscopy for tens of sources at a given time, simultaneously. So using fiber-fed instruments and positioners that identify the objects in the focal plane and put the fibers to transmit the light from individual sources into the spectrograph, where you disperse the light and then you can record with the detectors, okay? With these kind of telescopes and these kind of instruments, you can do maps of the distribution of the galaxies in the universe, for instance, by doing many observations. This was a pioneer instrument. Nowadays, there are other instruments in other telescopes that take 1,000 spectra simultaneously, and they build the spatial distribution of galaxies in the universe. And this is just a scheme where you can see, as a function of distance, how galaxies are distributed. Each dot is a galaxy, and you see how they cluster. In clusters of galaxies, they have vacuums or voids, regions where they are lower density of galaxies. These things, this kind of instrumentation allow us to explore the universe and try to understand how it is the structure in the universe. Of course, the biggest telescope in the Canary Islands, the Gran Telescopio Canaris, actually the biggest in the world, has been built here because of the good conditions of the observatory and because we had in Spain the technology to build most of it, not all of it, but most of it. And, okay, you have here views on this telescope, which has a particular feature. The primary mirror of this telescope is a collection of mirrors. There are 36 segments which are continuously operated to have perfect shape in order to produce extremely good optical quality. And these are the mirrors you can see there. And there are actuators that have been designed in our institute and manufactured in companies in Spain. And this all collection of mirrors provides this tremendous power for collecting photons. And then from here I will show how the light goes from the primary mirror to the secondary. It's reflected then into a tertiary mirror, which will distribute the light to different instruments. So in 10 minutes you can change from one instrument that measures in the optical to an instrument that takes measurements in the near infrared or in the mid infrared. That is the tertiary mirror, and around that there are a number of foci where we deploy the instruments that will record the images of the sky, of the sources in the universe, all right? So you see the different foci. We put instruments in each of these. Okay, so this is an overview of instruments. What about the atmosphere? The atmosphere, well, light propagates from the cosmic sources through the atmosphere, through an optical system to our detector, okay? And there is a very basic principle which gives you the spatial resolution of a system as a function of the wavelength and the diameter of the main optical component that collects the light. In this case is the primary mirror diameter. And you see, well, this is the shape of a point source after going through a perfect atmosphere or absence of atmosphere and through a perfect optical system. But the turbulence in the atmosphere is a limitation for the quality of the images that we take. And we are making a major effort to understand the turbulence of the atmosphere, how it disturbs the propagation of the wavefront, and how can we correct for those distortions and find out how to get what is the signal out of the atmosphere from the ground observatories. This is a cartoon to show how the turbulent surge disturbs the propagation of a perfect wavefront, and the distortion then goes into the focal plane, producing an image of a point source, translating that image into a collection of what we call speckles, features that make an image a little bit disturbed, okay? So we want to correct for that. And I'm saying this because here in the University of La Laguna, there is a group that works very very intensively in this kind of techniques, and we also in the Institute have now a long-term plan to do a major step in the quality of corrections that we can achieve with our telescopes in La Palma. This is a project that is starting and will go for the next 4 or 5 years until we really get a major improvement in our telescopes. Why we do this? We do this because with these techniques we can get resolve sources which otherwise the turbulence will mask. For instance, just 8 or 9 years ago, it was possible to obtain with the 8-meter telescope that Europe has in Chile. It was possible to resolve this little source from this bright spot here, just separated by 0.8 arc seconds. This is the first image of a planet taken on a source different to our solar system. So that first image has been obtained thanks to a system for able to correct the turbulence of the atmosphere. So that's why it is important, because under normal seeing conditions, this source would be immersed in a spot this big, okay? So with these corrections, you can see these little things. And we want to do that also from our observatories, where these techniques have not been much developed yet. For instance, if you are observing a nebula and you do a combination of adaptive optics with other corrections, then you can get this kind of very sharp images. You are going to a globular cluster where there are hundreds of stars, and you can, by implementing these corrections, you can do this significant improvement, and you can see things that otherwise you would not be able to see, okay? So the message is that advanced technology is very important if we want to really understand, understand what is going on outside the Earth. And for that, we not only we need very good ideas from the theoretical point of view, very good techniques to analyze the data, we also need very advanced technologies. And we are here, we're making a major effort to develop technologies to serve science at the Institute, okay? Telescopes, as the one I have described, the 10-meter instrumentation to do images or spectrographs, gratings, prisms, lenses, micromirrors, devices, the fibers. There are many high, very advanced technologies that we implement in our systems. And of course, from the mechanical point of view, actuators. The actuators on our mirrors or cemented telescope correct the position of the mirror at the level of hundreds of nanometers or better than that, okay? So you need very special things to do these things. Cryogenics, we need to put our detectors at very low temperatures to make them more sensitive, and it's a very complex thing to operate when you are working, for instance, close to 4 Kelvin, and there are many systems that require this. So detector technology, you need CCDs of different types for the optical, for the infrared, for microwaves. So all these things have an impact on the quality of the science that we can do. And that's why we put so much effort in doing good technology also in our research center. Being said that, I will go into the science just to give you an overview of the topics that I think are concentrating a major effort in our institute and also at large in the world, actually. So we want to understand the sun, our nearest star. These are images taken in X-rays. You see how ejections take place. The sun is a very quiet star as compared with many others, but you can see here that it's not so quiet. There are many things going on there. There is activity coming from the interaction of rotation with convection. It's a plasma formed by hydrogen and helium at high temperature. You know that in the interior you reach temperatures where hydrogen is burned. You get much higher temperatures. In the external, in the photosphere, the temperatures are about 5,800 Kelvin. Now you see this interaction of rotation and convection produces magnetic fields. And one of the major challenges in solar physics is to understand the generation of magnetic fields, how they evolve, how they are produced, and what are the consequences of the magnetic fields. You see these loops of material that, you can compare with the size of the Earth at the same scale. These loops are continuously produced. Even a small telescope that we have for divulgation can show these loops in the schools, and we are doing that. We take these solar telescopes to the schools and show the students there how these things happen in real time. But we really need to understand the physics of this in a lot of detail. We need to understand phenomena like the granulation in the solar photosphere, the emergence of solar spots, the generation of magnetic fields, how is the interplay with convection, and this requires magnetohydrodynamics, very sophisticated codes, simulations, and our people develop these codes and run these codes in the supercomputers in Spain and in any other place. So the sun is a major topic for research and will keep going for many years because we do not really fully understand what's going on in the sun. And as part of the long-term program of the IAC, we have a project that consists in building the European Solar Telescope, which is led by Professor Collados, professor of this university. And this telescope, if built, will be built in the Canary Islands, will be one of the largest in the world by the end of the decade. So there is a very active group working in that. The exploration of the solar system is really conducted, well, with observations from the ground, but a lot is done with missions, as you all know. Well, we have, just to keep in mind the relative sizes, we have the Earth here, okay, terrestrial planet, and a giant planet like Jupiter. These are the relative sizes. We explore planets in the solar system with missions. This is just a 3D real reconstruction of the surface of Mars. You can see the effects of the impacts of asteroids on Mars, quite obviously. The bombardment of planets by asteroids, well, had a maximum thousands of millions of years ago, but you know we are still under risk for a potential impact, so we keep going in this exploration of the solar system to identify all potential asteroids. And the catalogs have been built with the increased sensitivity, and telescopes are fully dedicated to that. Huygens was one of the amazing missions that ESA launched with the intention to visit Titan, which is this moon where there has been the mission, the probe get to the surface of the moon, and they were able to see the presence of hydrocarbons in tremendous amount. They don't have so much water. They have seas of hydrocarbons there. And this is just one example of the things that are being investigated, how this form, whether there is life in Mars underground or any sign of potential development of life in the past. All these are very hot topics in solar system research nowadays. And even with the Hubble telescope, just a few months ago, there were newly discovered moons, for instance, in Neptune. So we are still identifying all the components of the solar system. And this will continue for decades because we are far to have a full description of everything that is there close to us. Let's move to stars and exoplanets. That's a major topic for research in our institute. Stars like this that you see here in the cluster known as the Pleiades. Stars form normally in clusters. Hundreds of stars at a given time form. This is a system with an age of about 150 million years. The sun is something like 4,700 million years old. So that was a young cluster. In many stars, there are searches nowadays to try to identify the presence of planets. And one of the techniques that is more successful in this process of exploration of other planetary systems is the so-called Doppler technique or radial velocity technique, which measures very precisely the velocity of the stars. And if a star has a planet, then the wobbling associated to the gravitational pull of the planet, the wobbling could be measured because it could have amplitudes in velocity of meters per second, and we have the technologies to measure that. So just to remind you that Jupiter is able to induce an amplitude in velocity in the sun of 12 meters per second over a period of 11.9 years, and the Earth induces a velocity wobbling of 0.1 meter per second on the sun. So far, we have no technology to measure this, but we are working to produce the instruments that will be able in 2-3 years to measure this in other stars. So we will be able to see in the radial velocity curves of stars the influence of a planet like the Earth. The name of that project here, I show some of the pioneer instruments dedicated to these radial velocity searches. LOD, it's a simple spectrograph now, but at the time it was a pioneer in the sense that it was able to produce the best measurements of radial velocity of stars, and it produced the first detection of exoplanet, of a giant planet around a solar-type star in 1995. So that is the year where these researchers, Michel Mayor and Didier Queloz, in Switzerland, detected the first planet around a solar-type star. Now we know that there are more than 1,000, actually this is a little bit out of date, more than 1,000 exoplanets discovered, and more interesting is this sentence here. 30–40% of the stars, like the Sun, or a little bit lower mass than the Sun, host planets. And we are quite sure about this statement. So you can calculate the number of planetary systems in the galaxy. If I tell you that in our galaxy it's easily 100 billion of stars, all right? So the number of planets is tremendous. So the question that remains to be answered is this: how many host terrestrial planets we have? So we don't know, because we have not been able to really see planets like the Earth. We have indications that it could be very frequent. Some planets with the mass of the Earth have been discovered with a different technique using transits or eclipses of stars, but we don't know how frequent are planets like the Earth, not yet. We will know in a few years for sure, okay? So for the moment, let's leave this as an open question to which you can contribute in the near future. Now, what about direct imaging of exoplanets? I already showed the image taken in 2004 for this planet nearby a very low mass object. But years before, our group at the Institute found similar objects to the one I showed with adaptive optics, but free-floating in space, free-floating in star clusters. So the potential to obtain images of free-floating planets has been with us for 12 years already, because we did this in year 2000. And you see these points here, okay? This is an image of a free-floating giant planet in the sense that it's not associated to any star. This is a zoom of that. This is a super Jupiter. That's the way I define these objects. A super Jupiter, which is not associated gravitationally of the stars here, is just free-floating there. We are convinced now, and it has been detected last year, that in the solar neighborhood, they are free-floating giants or super Jupiters. And the first have been found by a satellite in the infrared, the WISE satellite, just at 15 light years from the Sun. But we discovered these things already in year 2000. And as I say, not only these objects are orbiting around stars, they are also free-floating in space. And we don't know very much about this. How we do imaging of planets around stars? Okay, we used advanced adaptive optic systems. Some of them have to be guided with a laser that is launched to the atmosphere to simulate a reference star. And we are starting to work now on a similar system that you see here in operation in the 8-meter telescope in Chile. We are working now to produce something similar in the Canary Islands for the 10-meter telescope. With these things, you can do, by using coronagraphy, you can search for planets. And here, that's a planet similar to Jupiter. The star has been masked. You don't see the star, but you see there is a planet, and you see that there is a disk of matter in this system, in Beta Pictoris, a disk of matter, which is aligned with the presence of the planet, okay? There was, for a long time, there was predictions that planets formed in planetary in disks of material, which are the remnant of the process of formation of the star. And there is increasing evidence that indeed this is happening. This is a planetary system directly imaged in one star, which is masked here, sorry. The star has been masked with a coronagraph, and you see super Jupiters of 10 Jupiter masses, 9, 10, 7, detected with the most advanced adaptive optics systems in the 8-meter telescopes that the United States have in Arizona, I think. The Gemini telescope. So this is the name of the star. The star you don't see, but the important thing is that it's the first fully imaged planetary system out of our solar system. Now these are images of Hubble that shows that things are very complicated. You have again the star masked by the coronagraph, and then you see this is the disk of material around the star, reflecting light from the star. But our colleagues in the Space Telescope Center were so, had the skill to see that one of these little spots here, which has been zoomed here, was moving around the star, year 2004, year 2006, and they claim that this is a planet which is in orbit around this, in addition to all this material that remains from the process of formation of the star. So this is a very, very well-known, Fomalhaut is a very well-known star that has been investigated for many years. There's a lot of work going on to get very high-quality imaging of planets, because we want to detect their presence, but we want to understand their atmospheres, we want to understand their physics, their chemistry. So the Keck telescopes, the two 10-meter telescopes, which are segmented, as the one in Canarias here, have a long-term program for interferometry to combine the light from the two telescopes, and since they are separated by 100 meters, then you get the spatial resolution equivalent to a telescope of 100 meters in diameter. The equation of lambda over d, that's what they basically are doing here, or we are doing, because Spain is also part of this, with the 8-meter class telescopes that are located in Chile, the 4 telescopes with some auxiliary equipment, they conform also an interferometer. Optical interferometry is extremely challenging. It has been a major effort without great success yet, but in the future we are convinced that they will produce very nice images where we will be able to see Uranus-like planets. But it's not yet the time. The technology has to be improved. So the big question is, when are we going to direct imaging of the stars or other Earths? Well, we don't know. Possibly in 10 years, possibly in 15 years, but it will happen at some point. We will not only see the effect of the Earth in the star, we will not only see the eclipses, which are already detected by Kepler, a space mission, we will directly see the Earths, okay, at some point. We need a larger diameter. For the current telescopes, it's impossible. For the next generation of big telescopes of 30, 40 meters, it might be possible in a few nearby stars. If at some point we build even larger telescopes, it will be possible to separate the light of the reflected light of a planet like the Earth from the nearby star, okay? And I remind you that the contrast in reflected light is 10 to the 9 for our Earth with respect to the Sun, as seen by an external observer. This is the ratio, and that's very difficult to resolve when the system is separated by just 1 second or less than that. This is the future European telescope, the telescope that may start construction next year in Chile. It's 39 meters in diameter, and it is a cemented telescope. It means that there are 500 mirrors, or a number of close to that here, with the same techniques that we developed here for the Gran Telescopio Canarias, okay? This will be the biggest telescope in Europe in 2020 or beyond, okay? And it's an effort of all the countries that belong to the European Southern Observatory, and Spain is involved in that. And Spain is part of one of the first instruments for this telescope, which is Harmony, and Professor Mediavilla is leading the participation of the IAC in that instrument. And he's sitting there. And okay, spectral biomarkers, that is the next step. When you separate the light from the planet in one way or another, what you want to see is what molecular features are there, okay? So We want to understand what temperatures, what is the physics of the atmosphere, and what molecular features are there. Do you have oxygen? Do you have methane? Do you have chlorophyll? Do you have what evidence for biological activity can we find there? That's an open question, and it's a question that I think will have an answer also possibly in the next decade. So at some point we want to find this kind of planets which resemble the Earth, and it's, as I say, one of the major challenges in astrophysics at the moment. Let's change the topic and go to the origin of stars and planets as large. This is a major topic for research. We want to understand why stars exist, why planets are formed around the stars or independent of the stars. So let me draw your attention to the fact that in the galaxies, not only there are stars, there are tremendous amounts of gas, hydrogen and helium mostly, that are present in the interstellar space. From this gas, you form the stars. And from that process of star formation, it's really a very complex process. This is Orion, the nebula. It's a very well-known nebula where thousands of stars are being formed right now. They have been forming for the last million years or so, and we can see that. We can see the gas, the clouds of material, and also when you enter with powerful telescopes, you can see the stars in formation. Very young stars, less than 1 million years old, as compared with the 4,500 million years old of our sun. That's really the very, very early stages of star formation. And you may note in these images of the Hubble Space Telescope, the little shadows that are there. These are protoplanetary disks. We know 95% of the stars show these protoplanetary disks. We think that most of them will form planets. I said that 30–40% of the stars we know have planets, but we see that the process of this formation is even more frequent. Okay? And this is a simulation made with supercomputers let me see if it works. Because it's interesting, how can we understand this process of star formation? Well, the equations that describe this are non-linear, are very complex, so the only way is through numerical simulations. Okay? You take 4,000 processors and you run for a few weeks the code under prescriptions, and you get how gas goes into stars. And you see the stars here. You see how the little dots are planets that are formed, and you see some of the planets, because of dynamical interactions, the simulation tells you will be expelled from the formation. So already these simulations, which were made after our discovery, I have to say, of free-floating planetary objects, these simulations explain easily that some of the planets remain in the disk of material around a star during the process of formation, and some of the planets are ejected. Okay? How frequent is one thing or the other? We don't know, because we have not been able to see in real time this process of ejection. But this is something that it may be possible to see in the next years using new technologies. We clearly see protoplanetary disks around the stars using coronagraphs and Hubble Space Telescope, and you see these disks around these stars. By the way, the size of these protoplanetary disks are sizes similar to the solar system size. With this kind of radio telescope, millimeter telescope, which is one of the many that conform this array of millimeter telescopes, the biggest built in the world, ALMA in Chile. It's an international collaboration where Spain also participates. With this kind of interferometer, it's possible to explore the formation process, and it's possible to see the disk of a protoplanetary system and the formation of the planets. And it has not been possible yet, but I think with a little bit more effort, it will be possible in the next years, using this interferometer, it will be possible to see, not only the disk of a protoplanetary disk here around a star, but also if some of these things that you see like little wobbles there, if any of this could be a planet. And then basically determine whether this process is taking place, the planet formation takes place where we believe it takes place, which is in this material around the stars. This is the beginning of a star. I will jump into the end of a star, and depending on the type of star, the end of the life is different. This is the end of the life of a star like our sun. Our star will end like this planetary nebulae. That's the name that has been given to these systems. They are very colorful, very beautiful, but at the end, these systems tell us that our sun will suffer a major transformation from being a normal star burning hydrogen. It will change the processes of burning in the interior. It will transform into a giant star. It will eject a large fraction of the matter, and this ejection of matter is what you see there. Its different colors are different atomic elements, oxygen and other elements, and this will get into the Earth, of course, and will cause a serious problem for the life in our planet. But this will happen in 4,500 million years from now, or something like that. So this will take a lot of time. Other stars have a much faster evolution, and in just a few million years, transform from a star, which is burning elements in the interior, to something about to explode and ejected a lot of matter. And this is one of the very much studied systems where you can see how in the last phases of massive stars, before the star explodes, a lot of matter is returned to the interstellar medium surrounding the star, and these colors again tell us about different elements which are produced, synthesized in the interior of such a big star, a star that could be tens of times the mass of our sun. Some of these stars produce the most energetic phenomena in the universe, supernovae and gamma ray bursts. And I'm going to mention a little bit about this, some features of this. Supernovae are well known to all of you. You have the classical example of supernova 1987A. You see this star here. A few minutes after, the star explodes and becomes one of the brightest sources in the Magellanic Cloud, and easily seen by eye at the time of explosion. So this is one of the latest events in our galaxy, a supernova event. Okay, the Magellanic Cloud is a satellite of our galaxy. So every 100 years or so in our galaxy, something like this happens. One massive star becomes a supernova, it finishes its life, and what is produced there is a lot of elements, a lot of matter is ejected and transformed thanks to the nuclear reaction networks that develop at billions of degrees, which is the temperatures that you can reach in this process. And matter is transformed, different elements are synthesized, as I say, and this is the remnant after the explosion of a system that happened hundreds of years in our galaxy. Okay? Cassiopeia A is a very well-known system where there was explosion, a neutron star was left, and the remnant of the ejected material can be seen with radio telescopes, with X-ray telescopes, with optical telescopes, infrared, etc. By investigating this material, you can learn what happens during the supernova explosion. But there are many things still not understood in these processes, which are simulated again in the supercomputers. What we see, for instance, this is the Crab Nebula, another explosion hundreds of years ago in our galaxy. The remnant of this is somewhere here. You will see it's a neutron star. In some explosions, you may form a black hole. We don't know yet when do you form a neutron star, when do you form a black hole. In this case, clearly there is a neutron star there because we can see it. Neutron stars, in some cases, when the alignment is good for us, produces pulses. In this case, it's every 30 milliseconds. There is a radio pulsar. They were discovered through radio observations, but this is imaging taken with our optical telescopes in La Palma and an instrument that was built in purpose by our group in the Institute of Astrophysics in collaboration with UPCT. And you see the pulsating source at 30 milliseconds. It's a movie, okay? But you see how it's pulsating because the alignment of there is a jet emerging from the neutron star, which is a system with, neutron star has only 15 kilometers in in diameter, okay? And there's a jet well aligned of ejection of material and of radiation. And every time that it's like a lighthouse, every time that it goes spin, you see it, and then that's the reason for the pulsation. So neutron stars are the densest objects that we know. Presumably black holes are even denser, but we don't see them, so we have to understand that a little bit better. But neutron stars are the densest states of matter. It means that they require equation of states that we have to define and are not fully understood yet, okay? So this is an interesting end for very massive stars. The other interesting end that they mentioned are black holes. And we know about several black holes, not many, 10, possibly 20 if we allow for the latest, about 20 black holes or so well identified in our galaxy, which are the result of stellar evolution. And this is a major topic of research because in the proximity of these black holes, you test general relativity. You test our best description of gravity, okay? And only for that, and not only for that, but just for this reason, you could invest a lot of effort to understand what's going on there and see whether we understand properly gravity, okay? How we detect these black holes? Well, we presume there are millions free-floating there, for which we don't know anything. But for these 20 or so, we know that they exist because they have a companion star that is transferring matter to the black hole. And this process of mass transfer produces ejecta like this, and sometimes pulsations, big eruptions that are detected in X-rays and in gamma rays, okay? The satellites that are monitoring, and I mentioned at the beginning, there are satellites monitoring the sky in X-rays because these sources come in eruption. Maybe a source takes 30, 40 years to get into this state and then become quiet, and then 30, 40 years, again an eruption. So when this happens, you detect with the X-ray monitoring telescopes, and then with the telescopes on Earth, you follow what's going on there, okay? And what you find is frequently, okay, that you have matter indeed approaching the system, being even swallowed by the black hole, or you find the star moving around very fast, and you produce studies of dynamics of the systems, and well, I think this helps to understand. I was going to say that there is you know that there is a journal in multidisciplinary science, that is Nature, that, well, I think very soon there will be a new publication, one of our colleagues sitting here in the audience, of a paper on a black hole that I cannot say much because these things are embargoed, okay? So the Institute has a very active work, research group on black holes, and there is a new discovery that will come in 1 month on this field, which I think is very, very relevant. Not only black holes are formed as a result of stellar evolution, black holes are present in the centers of galaxies. In particular, in the center of our galaxy, there is a black hole with a tremendous mass, which have been formed in a different way. I'm not sure we fully understand how these monsters form in the centers of galaxies. It's a major, major topic for research. You see in that image there the center of our galaxy. And this is the center of another galaxy. Just to tell you that what we see in distant galaxies is large jets of material at relativistic velocities that are just producing a lot of energy. And why is happening that? It's possibly because matter gets very hot when it gets close to the horizon of the black hole and gets a lot of energy from the magnetic field and becomes ejected. In the center of our galaxy, what we see is something different. We see that the stars that are in the center are moving around something. You see here, year 1992. It's a movie of real observations made by our colleagues in Germany, the group of Gensel, and you see how time goes on and how the motion of the stars is described by the observations. and this ellipse is already complete, and you see that there must be something in the focus of the ellipse where the gravitational potential is generated, which we don't see, okay? And you see a tremendous star, much bigger than the sun, much more massive, moving around something with the orbit of 10 light days, okay? To give you a reference, the distance between the sun and the Earth is 8 minutes light, okay? So that orbit is big, and the star is moving in a few years because there is a lot of gravitational potential. And the mass associated to that, not seen black hole, is 4 million solar masses, okay? So this is a challenge to astronomy. It's to understand what's going on, to find other stars that may be in orbit, fainter stars that may be in orbit, in closer orbit, and test how is the dependence with radius, for instance, of the distortion produced by the mass of the black hole. In the galaxy, we can do this thanks to adaptive optics observations again, advancing technologies that produce these nice images. So, just to go for the final part of the talk, I will move to galaxies, and from galaxies to the origin of the universe. So galaxies are collections, systems of billions of stars, as I said, and a galaxy like ours is this. It gives you an idea how is our galaxy, and where is located our sun. Well, our sun is located somewhere here. This is an image of a galaxy like ours taken by, well, this is Andromeda. Andromeda is similar to our galaxy. This is an image taken with a space observatory, Herschel Space Observatory, in a completely different wavelength. The previous one was observing the optical. This image is taken in the far infrared. And in the far infrared, you see these rings very, very clear where stars have been formed more intensively. These are rings of star formation, but you see there are many regions in the galaxy where stars are in formation. There are many other things going on. I have no time to describe that, but I wanted to show you basically an overview of how we are surrounded by galaxies. If you look at the scale here at the top of the following sequence of slides, you will see scales in this slide is 1 million light years. So then the galaxy I was showing was at a few million light years from our galaxy. Andromeda is one of the nearest similar galaxies to ours. Then we can move farther away just to have an overview of what is surrounding our galaxy. And, well, we see other galaxies, as I said. Let's move a little bit farther, 10 million light years, okay? And then you see that they start to appear some concentrations of galaxies. So we start to see clusters of galaxies, not only groups, but clusters of galaxies with hundreds of galaxies in each. We need to understand why. These clusters of galaxies are formed with a large variety of shapes of galaxies of different types, which I will not describe, but there is a tremendous rich variety of galaxies here. And but what I want to get is to the cosmic network. These clusters of galaxies tell us about not only about the properties of the galaxies, but also the properties of matter that we don't really see, but we see is present because it disturbs the propagation of light through the galaxies, so in the cluster. You see these arcs? These arcs are distortions of the propagation of light caused by matter distributed in the cluster of galaxies that produces gravitational deflection of the light of more distant galaxies in the far background, the far background of this. So clusters of galaxies tell us also that there is matter that we don't see in the universe, that is not forming galaxies, is there, and is there in a large amount, more than we can detect by the emitted light. We call this thing dark matter, and you sure have heard about this. Let's move at a different scale, 100 million light years. Then not only we see clusters, we see superclusters, we see structures with filaments in the distribution of galaxies and voids, volumes where there is a much lower density of galaxies. Why is this universe configured in this way? Well, that's one of the biggest questions that have to be resolved. This is, of course, a speculation. It seems that the full universe has this structure, what is called the cosmic web, okay? And as far as we have reached with the telescopes, we see that this cosmic web, this spider web, is there, okay? And we need to understand why. It's a major question. That's a simulation made on supercomputers again to show that indeed under basic principles, if we include a component of dark matter, of matter which is weakly interactive with normal matter, then you can reproduce what we see in the distribution of galaxies. And indeed, the simulations in computers show this filamentary structure. Let me show what is a simulation. I think in the next slide you will see. This is a three-dimensional projection of the structure, a simulated structure. And I will show later how this combines with this other thing, which is very important. We have a structure which is not static. We need to understand why there is this structure. We need to understand why the universe is not static, because we see it in expansion. We know that from Hubble. We know that from the 20s of the past century. That was the first article where he described the expansion of the universe, although I'm not sure he realized about that. We understand this plot with further measurements. We understand as a result of behavior of the space-time in the universe, okay? So this relation, which is very important, and comes from the work of Hubble, has been fully confirmed. Not only there is a relation between apparent velocity and distance of galaxies, but we know how combine this expansion of the space-time with the collapse of matter because of gravitational interactions to form the structures that we see in the universe. All this is, the scenario is relatively well understood, provided that two important facts that are not well understood are present. A large component of dark matter with little interaction with conventional matter, and a large component of what we call dark energy, okay? These two things are a topic of major research nowadays in many research centers, and they are really needed, because if you cannot produce this kind of simulations if you don't incorporate these ingredients in the simulation. And these ingredients contribute basically 95% of the total matter and energy in the universe, okay? And are very important. So I'm not sure we can really say that we understand everything. So there is a lot to be understood, but I think there are hints that these things are correct. And I will explain you why we need these ingredients for other reasons. Among the questions that remain to be answered is this: when the first galaxies formed in the universe, because the universe has not contained galaxies during the full lifetime. For that, you need big telescopes to see more distant, to see the early times of the galaxies, and Hubble will be substituted relatively soon by another telescope, which is this one, under construction, the major investment for astrophysics ever done. It's the James Webb Space Telescope, led by NASA, with a participation of 15% of the European Space Agency. That's, as I say, is the biggest investment in astrophysics. $6 billion is, I think, the investment that has been done so far. We will see what happens in 2-3 years when it is launched, and hopefully safely launched. It will be a revolution for infrared astronomy. Because of the diameter, 6 meters will give a very good quality imaging. Now let me go back to the point, the original point of what happened in the very early universe. And well, what we have is this global description for the evolution of the universe in expansion. You see how the universe is expanding here from sun original time. Well, how this has formed galaxies and so on, we basically understand if there is dark matter and dark energy, and there is this expansion. Even if the expansion is accelerated, as you know, there is evidence for an accelerated expansion. Why we are so sure that the things are going well? Well, there was a series of experiments, microwave telescopes, that have obtained images of the radiation of the early universe. And basically, you see these maps. These maps show the seeds of the formation of the galaxies. And the properties of these maps, these maps obtained first by COBE, then by WMAP, and now by Planck, the most recent one, which is this satellite, which has the involvement of Europe, is leading, the European Space Agency is leading this project, which offers all these qualities. With this has been possible, and we are part of this here at the ISE. We have been able to obtain, using these two instruments, LFI, HFI, two very complex instruments, as you can see here, working with cryogenics and advanced technologies. Well, we have been able to obtain not only the emission of the galaxy, but also the emission of the radiation from the Big Bang, which are these little spots here. We will need a full talk to explain what is the meaning of these maps, but I will tell you that thanks to this kind of observations, we really know that the model we have for the universe is a reasonable one. And this model, to explain the imprint in the microwaves that we receive from the origin of the universe, to measure this, to understand this map, we need indeed dark matter and dark energy. Anyway, what is going on and what remains to be understood? We know that the geometry of the universe at large scales is Euclidean, and this is something that comes from these experiments in microwaves and others that have been done. We know that. What we don't know is whether in the early times of the universe, gravitational waves were produced. And this is a major prediction for the Big Bang model that has not been confirmed yet, and it will be one of the challenges for the next years. How primordial gravitational waves will be measured? Well, it's possible to measure through the polarization of the microwave radiation. So, and a number of telescopes are being built to measure that. One of those telescopes is located here in Teide Observatory, and you can go up and see it whenever you want because it's already in operation. In the future, we may have to review this, but it seems quite solid, and I don't expect major changes, okay? We need to understand, we basically understand this little part of the pie. We don't understand the rest, but we know we need them, okay? It's not a very good circumstance, but that is life. So we need to understand what we know we need, okay? So let's go and talk a little bit about this and finish the talk. So what is the nature of dark matter and dark energy? I think it's one of the major challenges for the next years in astrophysics. How can we understand this? Well, there are a number of proposals, but the most important in Europe, in my view, is to search for the effects of this dark matter in galaxies or clusters. These distortions that you see in all these clusters, these distortions, these arcs are produced by that matter, by dark matter. And we know by doing better observations, we think that we can learn about the properties of this dark matter. Okay? And the other thing, how we learn about the dark energy, measuring the accelerated expansion much better than we have done so far. And for that, Europe has a big project. And I tell you because it's really big. There are 1,000 scientists involved in this project, okay? Euclid is the name of the satellite that will make a map of the deepest map of the galaxies in the universe, to see how they are distributed and how they have changed with time, the distribution in space-time. And this is fundamental to understand the nature of that energy. Unfortunately, Spain and our institute is involved in this project, which will possibly be launched around 2020. We are working hard to build the instruments to do the measurements we want to really understand the acceleration of the universe and to understand dark energy. But the basic message is that this satellite will measure the three-dimensional structure of the universe, as far as we can get with a telescope put on orbit in Lagrange 2, and measure the properties of the distribution of galaxies will be the key point of the telescope. Not the only thing it will do. It will do many other things, but the key science for this telescope. Okay? And for many of you, there will be opportunities to work in this in the next years. As I say, it's just starting, okay? So, to conclude, as a summary, well, challenges for astrophysical imaging, there are many. I just list a few, those that I like more, if you want, but it's subjective. I think we have the Earth-like challenge. It's very important to see other Earths and see whether there is biological activity in any of them. To image, in one way or another, black hole environments. This will require X-ray imaging, most likely, X-ray imaging, because then you get to the inner parts of the accretion disks around black holes. But there could be also observations like the ones in the center of our galaxy that can improve our understanding of black holes. The presence of gravitational waves, there are many ways to determine that. I just mentioned the polarization of the cosmic microwave background to see for gravitational waves produced in the major event of the universe, the Big Bang. But there are events in the supernova explosion that produce gravitational waves, and this can be measured in the near future, possibly. And finally, the evolution and the spatial distribution of galaxies to determine how the large-scale structure of the universe has evolved with time. All these things are challenges that will require astrophysical imaging. Thank you very much.